Hi guys, so today is our last day for square root and cube root functions. So what we're going to do is we're going to revisit inverses. Now we did inverses at the beginning of the year, but we're going to do it again because we have kind of an extra thing we need to consider now that we're looking at square root functions. So to start, we're going to start with kind of a basic one, just to kind of be refreshed on the process. The way we find an inverse is we switch x and y and we solve for y. So I'm going to rewrite this as x equals 2, 3y minus 4 cubed minus 5. So now we just need to solve for y. So I'm going to add 5 to both sides. I'm going to divide by 2. And just the way that I write this is I'm going to write it in kind of that transformation form. There's a lot of different ways that this equation can look and still be accurate. But I'm going to divide everything by 2, which is the same as multiplying by 1/2. And again, the reason I'm just writing it this way is because this is how we're used to seeing our transformations. All right, so now at this point, my next step to get rid of that cubed would be to cube root. So I end up with the cube root of 1/2 x plus 5 is equal to 3y minus 4. I can add 4 to both sides. And I can divide everything by 3. And again, instead of writing it over 3, which you could just say this over 3. It's not wrong. What I'm going to do is I'm going to write it as 1/3 times this, because that's just the format we're used to seeing for transformations. Now again, I also apply that 1/3 to the 4 and make that 4/3. And then the last thing, just remember the notation for inverse. It's f and then a little -1 of x. And that's the notation for inverse. So this would be the inverse of that original function. Again, inverse is when we have our x's and y's switched. All right, so now let's look at a different one. We're going to look at a quadratic. So it says to find the inverse of x squared minus 2. So I would do x equals y squared minus 2. So add 2 and square root both sides. Now the problem here is when you take a square root, we take both the positive and the negative. So let's go ahead and look at this on a graph. So I'm going to start by just graphing x squared minus 2. So I would shift down 2. There's no stretch, so it follows the normal parent function pattern. Right 1, up 1, right 2, up 4. And then if I want to go right 3 and up 9, I can as well. And then I would do the same thing on the other side. The only problem is it tells me to only graph when x is greater than or equal to 0. So I'm not going to graph this side. I'm only graphing this side. Well, now let's go ahead and graph our inverse. So just looking at our graph, okay, just looking at our graph, the way we find an inverse is we switch x and y. Well, this point was 0, -2. So my inverse should go through -2, 0. All right, this point is 1, -1, so the inverse goes through -1, 1. 2, 2 is still 2, 2. 3, 9, or 3, 7 would become 7, 3. So in purple, that is the graph of the inverse just from switching the x and y's from that blue graph. Well, if you look at that blue graph, or that purple graph, it's not both the positive and negative square root. It's only the positive square root. So I don't need to worry about both the positive and the negative because of this original restriction on my original function. Now, if that wasn't there, then I would have that whole graph, and I would also have this whole graph. So that whole graph would be both the positive and the negative. This top part is the positive square root of x minus 2. This bottom part is the negative square root of x minus 2. But again, because of that restriction, I only have the positive one. So if that restriction wasn't there, then the inverse wouldn't be a function. And then I'm just going to rewrite my inverse here with the right notation. So what that gets us ready for is when we start looking at the inverses of a square root graph. So what we need to consider, the graph that we have right here. All right, I'm going to go ahead and graph the inverse by switching the x and y coordinates of the points that I see. So I have 0, 5. So I'm going to flip that to 5, 0. I have the point 1, 4. So I'm going to change x and y and make that 4, 1. I also have the point 3, 4, which would become 4, 3. Sorry, I have 4, 3. That's going to become 3, 4. And the last point I have is 9, 2, which will become 2, 9. So my inverse are these purple dots right here. Now, if you look at it, it looks like half of a parabola. And we'll get into that, and you'll see it's going to end up being just that. All right, so what we're going to do now is we're going to write the domain starting with the domain of f of x. So f of x is the original function. So our domain, the farthest left is 0, and then it keeps going to infinity. The range for f of x, the lowest point at the bottom is negative infinity. It keeps going to 5. Well, now let's do the inverse. So the inverse is our purple graph. The domain of that inverse is from negative infinity until the x value of 5. The range of that inverse, bottom to top, is from 0 to infinity. And we talked about this the first time that we did inverses, and you'll probably notice it again. The domain of the original is the range of the inverse, and the range of the original is the domain of the inverse. So that is always going to be true. So what that means, let's go ahead and write the equation for f of x. So this is good practice since we just did graphing. So the equation for f of x, that graph has been reflected over the x-axis. So I need a negative on the outside. It's been shifted up. It has not shifted left or right. So I got a plus 5 on the outside. And then if you look, it follows the normal parent function pattern. Right 1, down 1, right 4, down 2. So it follows that same pattern. It hasn't been stretched or compressed in any way. So this is the equation of f of x. Well, let's solve algebraically to get f inverse. So I would do x equals negative square root of y plus 5. So x minus 5 is negative square root of y. So then I can go ahead and I'll square both sides. And I'm going to go ahead and leave that squared because, again, that's similar to what we see for transformations. I'm not going to FOIL it out because it's just easier to graph in this form. So that's my equation. But if you notice, look at the graph that we actually made. The graph that we made in purple, it looks like that equation. It looks like a quadratic that's shifted to the right 5. But it's not the whole quadratic. I don't have this part over here. The domain is restricted. So my inverse is the function x minus 5 squared. But I have to include that domain restriction because, again, it's not the entire parabola. So the domain that I actually have is the range of the original. So that is x is less than or equal to 5. So whenever we write the inverse of a square root function, we're going to get a quadratic as a result. But what we need to remember, it's not the whole quadratic. That quadratic is going to have a restricted domain. All right, so let's look at a couple more. So again, let's just start with domain and range, all right? So we'll start with the domain of the original. Well, the domain of the original, we take whatever's under the root and set it greater than or equal to 0, just like we did for inequalities. So 3x minus 2 is greater than or equal to 0. So x is greater than or equal to 2/3. So in interval notation, that would be from 2/3 to infinity. The range, let's think about our range for a little bit, okay? This function has not been reflected. It's been shifted up 7. So it's going to look something like this. So our range, the lowest point is 7. It has not been reflected, so it keeps going to infinity. Well, now, without even finding the inverse, we know the domain and the range of the inverse. The range of the original is the domain of the inverse, and vice versa. So the important part is right here. When we find the inverse, we need to include this domain restriction. That domain restriction comes from the range of the original function. Now let's go ahead and solve algebraically for our inverse. So I'm going to switch x and y, subtract 7, square both sides, And again, when I square both sides, I'm going to leave it in that form because, again, that's how it looks like when we do our transformations. So we'll add 2 and divide everything by 3. And again, I'm going to write it as 1/3 because that's just the way that we're used to seeing it with transformations. And again, I'm dividing everything by 3 or multiplying everything by that 1/3. So this is my inverse. But again, that's a quadratic. The original has this shape, a quadratic has this shape. Okay, it's not the whole quadratic. We have to restrict the domain. That domain restriction is the same as the original function's range, which is, in this case, x is greater than or equal to 7. We have to include that as part of our solution. All right, so let's just do a couple more for practice. Let's go ahead, we'll flip x and y, and we'll solve for y. So on this one, I would do x equals negative y squared. We'll go ahead and divide by -1, square root both sides. And when we square root, again, it could be plus or minus. Well, to figure it out, this is the original function's domain, which means that's f inverse's range. So the range that I need is going to be from -infinity to 0. Well, that's going to be the negative square root. All right, let's look at a square root function. So x equals 2, square root of y minus 3, divide by 2, square both sides, square everything on the left side, add 3, and I have my inverse. But remember, it's a quadratic. It's not the whole quadratic. So I need to find the range of the original. Well, that function has not shifted up or down. So the lowest point is 0. It has not been reflected, so it's going up, so 0 is the lowest point. So that's my range, which means that's the domain of f inverse. So my inverse is 1/4 x squared plus 3, and I include the domain restriction, x is greater than or equal to 0. All right, let's try a few more. So again, let's start by switching x and y. Add 2. Square both sides. I'm going to leave it in that squared form because it's easier to see your transformations. Multiply by 4. Add 3. And divide everything by 2, okay, including the 4 and the 3. Now again, started with a square root, have a quadratic. We need to include our domain restrictions. The range of our original function, it's shifted down 2, has not been reflected, so -2 is the lowest point. It continues to infinity. That is the domain of f inverse. So our inverse is that same function, but we include the domain restriction, x is greater than or equal to -2. All right, if you feel pretty comfortable, pause the video, try the next one. All right, let's switch x and y. Subtract 1. Divide by 4 or multiply by 1/4. Square both sides. I'm squaring everything. So this would be 1/16, x minus 1 squared. Add 3. Divide everything by 2. So that means I divide the 1/16 and I divide the 3. Now again, I need to include my domain restriction. The original function's range was from 1 to infinity. It's shifted up 1, has no reflections. So this one is going to be x is greater than or equal to 1. All right, so the next two examples, these were only on the GT notes, so honors, if you want to skip ahead a few minutes, you can. So what we're going to do here, we're going to go ahead again, switch x and y. So x is equal to y squared minus 6y plus 1. Now the only problem here, it's going to be a little hard to solve for y. I can't really factor it out because I'm still going to have a y there. So what I actually need to do instead, I'm going to complete the square. And that's going to be the easiest way to get that y isolated. So I'm going to subtract 1. I'm going to leave a blank. So remember, when we complete the square, middle term divided by 2 squared. So 6 divided by 2 is 3. 3 squared is 9. So add it to both sides. So that gives me y minus 3 squared is equal to x plus 8. At this point now, it's really easy to find the inverse. We just square root and add 3. And again, it is the positive square root because our original domain, that's our range that we're looking for, and that range would happen with the positive square root. So whenever we have quadratics in this form, we're going to need to complete the square in order to get our inverse easier. Now, whether you do it at this step or if you do it the very first step, it doesn't matter. You can do it either way. So on this one, I'm going to go ahead and just rewrite this in vertex form. So I'm going to factor out my 9. So what's going to go in my blank is going to be 2 divided by 2 squared, which is 1. But if I add 1, I'm not really adding 1. I'm adding 9 times 1. So I have to subtract 9 as well. And again, I have not tried to find the inverse yet. This is still the original function. So the original function can be rewritten in vertex form this way. Well, now let's go ahead and find our inverse, because it's going to be a lot easier from this form. So x equals 9, y minus 1 squared minus 4, add 4, divide by 9, square root both sides, and add 1. And again, we can consider the positive square root because the original domain was x is greater than or equal to 0. That means our inverse's range will be y is greater than or equal to 1. And that happens with that positive square root. It's also a good way to help us check our answer. All right, so the next thing that we look at is actually the wrong slide. Here's the right one. It's actually a pretty simple thing, and this is just a little trick to help us know, hey, will my inverse be a function? So if a function is 1-to-1, okay, it's special terminology. If it's 1-to-1, it passes something called the horizontal line test. So very similar to the vertical line test to determine if something is a function. Let's say I have a graph that looks like this. All right, it is a function. It passes the vertical line test. It does not pass the horizontal line test because a horizontal line touches more than one point. What that means is that function was not 1-to-1. If it's not 1-to-1, then the inverse will not be a function. So if a function passes the horizontal line test, the inverse will be a function. So this question is not telling us to find the inverse, it's just asking, is the inverse a function? Well, absolute value looks something like this. That would not pass the horizontal line test. So the inverse of absolute value is not a function. Cube root, okay, that general shape, something like this. That does pass the horizontal line test. The inverse is a function. It's a cubic function. And then quadratics, like we've already talked about. This quadratic, well, really it's going to be over here, does not pass the horizontal line test. So its inverse is not a function unless we restrict the domain. Which is why usually when we're finding these, you'll see the additional statement of x is greater than or equal to 4. Because if we do something like that, then the function we're looking at does pass the horizontal line test, and its inverse is a function. It's that square root function. All right, so the last thing we're going to look at is just reviewing how to prove that functions are inverses using composition. So again, we did this earlier this year, but what we can do is we can evaluate f of g of x and g of f of x. If both of those work out to be x, then that proves that those two functions are composition. This is a good way for us to check our answers and also just to justify what we've done. So we'll start with f of g of x. That means I replace the x in the f of x function with the g of x function. So this would be 3 times 1/3 square root of x minus 1 squared minus 1. Well, if I do that math, I would get 3 times 1 over 9 times x minus 1, which would be 1/3 times x minus 1, which is 1/3 x minus 1/3 minus 1, which is not x. So at this point we know, no, these functions are not inverses. All right, now let's try the next one. Let's evaluate f of g of x. So I would replace x with the g of x function. So 5x cubed minus 9 plus 9 divided by 5. All right, so negative 9 plus 9 goes away. So I'm left with the cube root of 5x cubed over 5. The 5's go away. I get the cube root of x cubed, which gives me x. So the first one works out. Now we got to try the other way, g of f of x. So again, this time, I'm going to take the f of x function and replace x in the g of x function. So this would be 5 times the cube root of x plus 9 over 5 cubed minus 9. Well, cubing a cube root makes it go away. And I wrote the original question wrong. That was not minus 5. This was minus 9. Then 5 times something divided by 5, those 5's go away. X plus 9 minus 9 is x. So both f of x and g of x were equal to x. So yes, these two functions are composition. These two functions are inverses. All right, so that is it for inverses part 2. Again, the same thing we've been doing, just be careful. You need to include those domain restrictions when you're starting with a square root and you're getting a quadratic as the inverse.